My name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is row space, column space, null space of a matrix. Before I talk about matrices and vector spaces associated with them, I want to remind you of what subspaces are. And I will limit myself in this lecture for subspaces of Rn. So if you have a subset of Rn W, then it's called a subspace of Rn if it satisfies three conditions. First of all, if the zero of Rn, the vector with all zeros, the n tuple with all zeros is in W. Secondly, if it's closed under addition, meaning that if you take two elements in W and add them, you stay within W, and it's closed under scalar multiplication. If you have an element of W and a scalar and you multiply them, you still stay within W. Watch previous videos if you're not familiar with these concepts. If you take a bunch of vectors in Rn, the span of those vectors, well, by that we mean all the linear combinations of those vectors. So if V1 through Vk are elements of Rn, then the span of V1 through Vk is all linear combinations of V1 through Vk. Linear combinations means you multiply V1 through Vk by scalars, maybe different ones, maybe the same ones, add them together. Anything like that, it's called a linear combination. And the span is always a subspace. Why? Because the zero vector is a linear combination of those guys. You just use scalar zero. If you have two linear combinations and add them, then you combine the like terms and you will again get a linear combination of V1 through Vk. And if you take a linear combination multiplied by scalar, you continue to have a linear combination. The set of all linear combinations of set of vectors is called the span, and that's always a subspace. If you have a subspace, and if you have a set of elements within that subspace, you have two conditions. If the span of S is W, those vectors, their linear combinations give all of W. And if S is linearly independent, by definition, linearly independent means that none of the vectors is a linear combinations of the other ones. Or another way of saying it is that there's no way to write a linear combination of all those elements of S equal to zero without cheating and without using just scalar zero for all of the vectors. If you have an S like that, where it spans and it's linearly independent, then you say that you have a basis for W. And an amazing fact that requires proof was done in previous video. All bases of a vector space have the same number of elements. And that size is called the dimension of W. So the dimension of W is the number of elements in a basis for W. Now let's start with a matrix. The purpose of this lecture is to introduce some fundamental vector spaces that are associated with a matrix. So I'm going to define three vector spaces for a matrix. So a matrix walks through the door. Previously, you might have thought of this as a bunch of numbers organized in a certain way. But from now on, after this lecture, when you see a matrix walk through the door, you will immediately say that there are three vector spaces that I should be thinking about. This matrix is M by N. It has M rows and N columns. These vector spaces that we're going to associate with it are called row space, column space, and null space. Our purpose is to apply our understanding of vector spaces, things we know about dimension, about spanning, about linear independence, and so forth, to these matrix vector spaces, these vector spaces that come from matrices. The row space, what is that? Here's a matrix, which is M by N, and I've also indicated its rows by R1 through Rm. So the rows, each one of those R1 through Rm are not a number, but they are a row vector. Each of these row vectors are themselves an element of Rn. This matrix is M by N. It has M rows, but each row has N entries because there are N columns. So each row is an element of Rn. So for example, if you look at the second row, alpha 21, alpha 22 to alpha 2n, if you just focus on that, you get an element of Rn. And on all the rows, we're calling R1 through Rm. Again, there's M of them. And the row space of A is the span of those. So you take the rows and you see what they span. What are all their linear combinations? That will be a subspace of Rn. There's M of them, but they generate a subspace of Rn because every one of them is an Rn. And that's called the row space. And the dimension of the row space is called the row rank of A. So matrix walks in, you look at the rows as elements of Rn, you see what they span. If you can find a basis for them, then you will know what the dimension of that is. And then that dimension is the row rank of A. Continuing on, what's a column space? Is very similar. I have this matrix A, which has N columns, again, M by N. And each column is an element of Rm. There's n columns, but each of them has m entries in it, and it's an element of Rm. Like for example, the second column, again, if you look at it, it's alpha 1, 2, alpha 2, 2 to alpha m2. I'm calling that C2. There's m entries in that, and that's an element of Rm. So all the columns are going to be called C1 through Cn, n of them. The column space is the span of those. It's all the linear combinations of those columns. The column space is a subspace of Rm. It doesn't live in the same place, in the same world that the row space lives, unless the matrix is square. The rows live in Rn. The row space is a subspace of Rn, but the column space is a subspace of Rm, a different vector space. And the dimension of the column space is called the column rank. And finally, null space, which is something we actually have seen before in previous lectures. So again, we start with the same matrix, m by n matrix. We have X to be a column of unknowns. Then AX equals 0 is a system of homogeneous linear equations. Again, we've seen in the previous lectures that if you have a system of linear equations, you can translate that to a matrix equation. And AX equals 0 is a system of homogeneous linear equations. Homogeneous because the right-hand side is all zeros. And what the null space is the set of all solutions to AX equals 0. So all the vectors X that solve this system, that when you plug them in, A times X becomes 0, that's called the null space. And notice that X has to be n by 1 because the matrix is m by n. And if you're multiplying A by X, m by n, you have to multiply it by a matrix that's n by something. And if you want a column vector, then it's going to be n by 1. That means that the null space is a subspace of Rn. The null space lives in the same world as the row space. The column space lives somewhere else. And the dimension of the null space is called the nullity of A. I'm going to tell you why is a null space a subspace. A is an n by n matrix. X is an n by 1 column vector of unknowns. AX equals 0 is a homogeneous system. Because it's m by n, there's m equations and n unknowns. Note when I write AX equals 0, that 0 is not the number 0, but it's a column vector with m zeros. It's the 0 of Rm. The null space of A is the set of solutions. That's what the definition was. Now, how do I prove that it's a subspace? Well, I have to show you that the 0 vector is there. It's closed under addition. It's closed under scalar multiplication. Well, first of all, A times 0, if you take the matrix and multiply it by a column vector of n zeros, you will get the 0. So that tells you that if you plug in 0, you get 0. So 0 is a solution. So 0 is in the null space. If a vector walks in and says, I'm in the null space of A, how do you decide if they're telling the truth? Well, you just take A and multiply them by that vector. And if you get the 0 vector, then they are in the null space. So 0 is in the null space. If X and Y are in the null space, is X plus Y in the null space? Well, what does it mean to say X and Y are in the null space? It means that if you plug in X or Y into the equation, it works. So that means that AX is 0 and AY is 0. Now, if I add these two things, will I also get something in the null space? Well, how do I know if it is in the null space or not? Again, I plug it in. So I look at A times X plus Y. I'm plugging in X plus Y. And matrix multiplication is distributive, has the distributive property. So that's AX plus AY. AX and AY were both zeros. So I get 0. So that tells me that null space is closed under addition, that X plus Y is indeed in the null space. And the same thing with scalar multiplication. If again, X is in the null space and alpha is a real number, then A times alpha X is the same as alpha times AX. In matrix multiplication, that alpha, that one scalar, doesn't matter if you put it before or after. That's one of the properties of matrix multiplication. And alpha X was 0. So again, you get 0, showing that alpha X was in the null space. And therefore, the null space of A is also closed under scalar multiplication. And that means that null space is a subspace. So this was using the matrix notation, proving that the null space is a subspace is pretty straightforward. Again, there was a previous video. We did that in terms of systems of equations, not thinking of matrices. And this is a much more streamlined version of doing that. Again, showing the efficacy of using matrix notation and matrix equations. Now let's look at an example. First of row space. This matrix is 3 by 4, 3 rows, 4 columns. Each of the rows, the 3 rows, are an element of R4. There are 3 rows, but each of them have 4 entries, and they're elements of R4. So for example, there is the first row. 1, 1, 3, 4. And I'm going to call that R1. And there is the second row, and that's going to be called R2. And that's the third row, and that's going to be called R3. The row space is the span of these 3 row vectors, R1, R2, and R3. What is a basis for the row space? These 3 vectors span it. Their linear combinations give us all the elements in the row space. But what's a basis for row space? To have a basis, you have to also have not only a spanning set, but a linearly independent set. But we have a theorem called the contraction theorem, a previous video, that tell you that whenever you have a spanning set in a vector space, you can contract it to a basis by virtue of going through the elements and one by one asking, from the first element, you ask, are you the 0 vector or not? And from all the subsequent vectors, you ask, are you a linear combination of the ones before? You put them in some specific order. And if the answer is yes ever, you throw that vector out. By the time you get to the end and all the answers are no, you have a basis. So here we ask, the first vector, is that the 0 vector? No, it's not. It's not the 0 vector. The 0 vector would have been 0, 0, 0, 0. It's not. Is the second vector, R2, a linear combination of the first one? No, you can't multiply the first one by scalar and get that second vector. Is R3 a linear combination of R1 and R2? Well, let's think about that. Can I write this 2, 3, 5, 7 as a linear combination of 1, 1, 3, 4 and 0, minus 1, 1, 1? Well, if I'm going to do that, how am I ever going to get that 2? Well, I could if I multiply the first row by 2, but I have to do that. So multiply the first row by 2, you get that 2. But then how am I going to get this 3? If I multiply the first row by 2, I already have a 2 in the second coordinate, but I need a 3. So I will have to multiply the second row by minus 1. And that will give me that 3. But will the other ones work? Multiply the first one by 2, by second one by minus 1. 6 minus 1, that's indeed 5. And 8 minus 1 is indeed 7. So that tells me that R3 is 2R1 minus R2. So R3 is a linear combination of the ones before. That means that it's not needed as a part of the span. And so we throw it out. And now because we got to the end, our contraction theorem tells us that R1, R2 is a basis for the row space of A, and therefore the row rank of A is 2. R1 and R2, those 2 vectors, span and are linearly independent. So the row space is this 2-dimensional subspace. It's a plane in R4. Now let's look at the same matrix, but let's this time look at its column space. A continues to be 3, 4. Nothing changed in that regard. But now it has 4 columns, each of them an element of R3. So the first column I'm going to call C1, that's 1, 0, 2. The second column I'm going to call C2, that's 1, minus 1, 3. The third column, 3, 1, 5, is called C3. And 4, 1, 7 is called C4. And the column space of A is the span of these 4 vectors. So the span of C1, C2, C3, and C4. But what's a basis for it? Well, I've got to go through the elements again and use the contraction theorem. C1 is not the 0 vector. I'm good there. C2 is not a multiple of C1. I'm good there. But again, you have to look at them, but you can do that. It's not too difficult to see that C3 is actually 4C1 minus C2. So we don't need that as a part of a spanning set. I mean, it could be there if you just were looking for a spanning set, but if you want a basis, it shouldn't be there. And so we throw it out. Also, C4 is 5C1 minus C2, and that needs to be thrown out. And when we do that, we are left with a basis for the column space, which consists of the first 2 columns, C1 and C2. So this means that we have a subspace of R3, a 2-dimensional subspace of R3. So this is a plane through the origin. A plane through the origin is the column space, and the column rank of A is 2. The row rank and the column rank were the same. Is that always the case or not? That's actually not at all obvious, because if you have a matrix, for example, that's 5 by 47, you have 5 rows and 47 columns in different worlds. Why would they be the same? They indeed are the same. That's spoiler alert. But that will need proof. Will come in not the next video, but a couple of ones down the road. There will be a proof of that row rank is the same as the column rank, always. Okay, so null space, and because of that, we actually call it just rank. So same matrix, let's find its null space. This is something we've done before. It's a 3 by 4 matrix. X is going to be XYZW, a column vector of unknowns. what we have to do is look at AX equals 0, which is a homogeneous system of 3 equations and 4 unknowns. And we have to solve it, and the solutions will be the null space. So the null space is the solution set, the set of solutions to AX equals 0. To find the null space, we have to solve the system. And how do we solve a system of equations? Well, we take the matrix, we write the augmented matrix, but here, because the augmented matrix has only zeros on the other end, we could just do the matrix, and we find a reduced row echelon form of A. So we do elementary row operations and think we get to reduce row echelon form of A, Gauss-Jordan elimination, or what I like to call the methods from the 9 chapters. You get the reduced row echelon form of A, and this gives you an equivalent system to the original one, and you solve that. And then at that point, the columns that do not have a leading one are non-basic variables. There are free variables. You can let them to be anything you like, and you can solve the columns with a leading one in terms of them. So if you do that, what you will get is that the null space is this set of vectors in R4. So again, the last two entries, that the Z and W, or R and S, they're arbitrary real numbers. But then from the second equation, we can get that Y is always going to be Z plus W, because Y minus Z minus W equals 0. So you take the other guys to the other side, you get Y equals Z plus W. And likewise, you get that X is minus 4 Z minus 5W. So because you had let R and S be Z and W, you get minus 4R minus 5S. So these are these guys. And then we know how to find, we have seen in previous videos, how to find a spanning set. You just let R be 1 and S be 0, and you will get a spanning set. And in this case, that happens to be linearly independent. So if you put R equals 1 and S equals 0, you get minus 4, 1, 1, 0. And if you put S equals 1 and R equals 0, you get minus 5, 1, 0, 1. Why is this a spanning set? Well, because if you multiply this by R, the first one, and the second one by S, and add them, you get the typical element of the null space. And because there are 2 vectors, and the first one is not 0, and the second one is not a multiple of the first one, a scalar multiple of the first one, it is a linearly independent set, and it's a basis, and therefore the nullity of A is also 2. Now, from this example, you might think, well, you might think that the row rank, column rank, and nullity are always 2. Well, that certainly won't be true. It also will not certainly be true that the nullity is always the same as the row rank and the column rank, but it will be true that the row rank and the column rank will be the same, as we will prove in later videos. So we're done with that. But what's on our agenda? One is to translate some of the things that we have been doing to statements about these vector spaces of matrices. So we have, for example, we have talked about solving AX equals B, which is a system of linear equations, not necessarily homogeneous. And that there's some relationship between that and, in fact, which B's can work for AX equals B in terms of the column space. That will be the next video, will be about the relationship between column space and solving AX equals B, a system of equations. Another very useful thing that we will do in a separate video is to look at what's the effect of elementary row operations on these matrix spaces. If you have a matrix and you have its row space, column space, and null space, what happens when you do some elementary row operations? Will those things change? How they change? Will they not change? And one thing I've already mentioned is, why is row rank equals to column rank? If you just think of, row rank and column rank are something that you can explain to someone like when we're walking down the street. You can tell, okay, look at this matrix. How many of the rows are linearly independent? How many of the columns are linearly independent? Somehow or another, those 2 numbers are the same. Tell me why. They won't be able to tell you if they don't know linear algebra. And finally, I said that the column rank is the same as row rank. We were going to prove that. And I said that the column rank doesn't have to be the same as the nullity. But not being the same is not the same as not having any relationship. Is there any relationship between the two? And the answer to that is yes. And that's a more subtle relationship, but very important one, that will also be subject of something called the dimension theorem. This is the end of this lecture. Keep hydrated and always. And I will see you at the next lecture.